Hi everyone, this video will be about interference of light. To some extent you have already seen interference. For example, when we were talking about simple harmonic motion, we talked about how two waves that look like, let's say this, so one simple harmonic motion that looks like this, and then let's say there is another simple harmonic motion that looks like this. If I put these two waves together, then I could get a wave that is sort of um, larger in amplitude, but sort of with the same period, etc. So we have sort of seen combining two waves to get a different wave. And the idea of interference is exactly the same. In the case of light, what we are going to be interested in, the kind of interference we are going to be interested in, is when the two rays with the same lambda and same frequency interfere with each other. Okay, and not only that, this interference should happen at the same place, right? So you have to sort of think about the same x and same t for this interference to happen. Because then if the interference happens at the same x and same t, this we can observe the effect of that interference, right? So that's our goal. So the first topic for interference will be interference from thin films. So in this particular picture over here, I have a ray of light that is coming in, so I'll call it incident ray I. I comes in, it is incident on the interface between two media. Let's say this is air and this is something else with refractive index n, which is so n is not equal to 1, right? It's different from 1. So this is a different material. This material can be glass or water or just a thin coating on the surface of glass. For example, if you have noticed tinted windows in your car. So that's essentially a thin covering over over the glass windows in your car. All right, so what happens when light is incident at the surface? Well, first a part of it gets reflected and a part of it gets transmitted. Now this transmitted part is going to be incident again on a second surface, a surface of interface between the material that we're considering and some other material, and let's give it a name N2. And generally, the property of N2 would be important, but the number N2 will not be important in our case. We'll see why in a second, but you can now see that this second ray of light will get reflected. A part of it is going to get reflected. Of course, a part of it is also getting transmitted, and we do not really care about this transmitted part. The second reflected part now, when it is incident on this air and material surface one more time, it's going to get um, part of it is going to get reflected, and this reflection will again not care about it so much, but a part of it gets refracted. Now you can see that the two parts that got reflected from the the reflection from the first surface and the transmitted from the second reflection, these two rays of light, they have the same frequency, the same wavelength, and they're also traveling parallel to each other, so there can be spots where the x and the t values are the same, right? So these two rays of light can interfere with each other. So if these two rays of light can interfere with each other, that interference pattern is probably observable. And in this case, since these are real rays of light, you can put a screen over here and you can observe that interference. And that's the idea for interference of light. And so what's going on here is that if you think of the ray of light coming in, its electric field is fluctuating like that, and the ray of light that is going out, that is also has a fluctuating um, electric field, and these are the two electric fields that are interfering with each other. Okay, so although this particular diagram has been drawn in a way so that the angle of incidence is not really 0 degrees, so the ray of light is incident obliquely to the normal. In our cases, we are only going to consider situations where the rays of light that are incident very close to the normal. And in fact, we'll consider the cases where the ray of light is incident normally. So take, for example, this situation, right? So, this is the ray of light that is incident, I. This first one is the ray of light that is incident. And then there's a ray of light. Of course, it's happening at the same spot, but just to show you that there's a distinction, I've moved the reflected ray a little bit further down, right? So this is the reflected ray, of light from the first surface, and then once the part of the light that goes through gets reflected over here, comes back, and then gets transmitted over here. So let's call that transmitted. And then the interference can happen between this transmitted and the reflected ray over there, right? That's the idea. Okay, so why could interference happen? So let's sort of get to the mathematical basis for interference. Okay, so in order to get to interference mathematically, let's start with two waveforms that are of this form. So I will start by saying that there is a wave that looks like A sine kx minus omega t plus delta 1. And then I have another wave that is A sine kx minus omega t plus delta 2. So you can see that both of these waves are traveling in the same direction. Both are traveling in the toward the right direction in the xt plot, and they have different phase constants, right? So these delta 1 and delta 2 are phase constants. So they have a phase difference, right? Phase difference. So because they have a phase difference, when I add these two together, so for a normal observer who's looking at x as same x and same t, the normal observer is not just seeing individual waves, he or she is looking actually at a sum total of these two waves. So in order to see what we would see, we'd have to check what is the sum total of these two, and then we'll have to do this kind of a addition, sine kx minus omega t plus delta 1 plus sine kx minus omega t plus delta 2. And now if you remember trig relationships, you can simplify this thing. So just to remind you, sine of A plus sine of B, this is equal to 2 times sine of A plus B over 2 times cosine of A minus B over 2. And here the order of A and B does not matter because A minus B and B minus A both will give you the same result, as the cosine of a negative of an angle is the same as the cosine of an angle. So cosine of theta is equal to cosine of negative theta. So it doesn't matter whether the A comes first or the B comes first, right? So essentially what this tells us is that if I simplify this, the equation that I have over here, right, this is going to give me 2 times A times sine of kx minus omega t plus delta 1 plus delta 2 divided by 2, right? So that's this part, A plus B over 2. And the other part, the second part from here, this cosine A minus B over 2 is going to give me a cosine of, here the kx minus omega t will cancel from both, but we'll be left over with a delta 1 minus delta 2 over 2, and we can call this delta delta, right? So it's the what is called a phase difference between the two um, waves. Okay, now it's generally true that if I look at this sort of an equation, then the amplitude of the resulting traveling wave. Remember, the traveling wave part is only this because that's the part that is kx minus omega t plus some phase relationship. Then the amplitude of this quantity is just 2 times A times cosine of delta delta over 2, right? This does not depend on depend on x or t, which means that at any x or t, you can always observe the effect of this. Okay, so the other thing that one has to remember is that you don't really observe amplitudes. Our eyes, with light rays or even with sound rays, we actually are observing the intensities. The intensities are really the physical quantities that are observables, and intensity is always proportional to the amplitude squared. So because it's proportional to amplitude squared, the resultant intensity, if I wanted to write I resultant, that's going to be equal to 4 times this A squared is just the I, so I can write I times cosine squared of delta delta over 2. Okay, so the intensity, now you can see as delta varies, as I change delta, at the same x and t, I can get different values of I resultant. And in particular, if delta delta is equal to pi or 3 pi or 5 pi, etc., if we put it back in here, we get I resultant equal to 0. right? I resultant equals 0. And on the other hand, if delta delta is equal to 2 pi, 4 pi, etc., then again, you can see that this I resultant quantity is going to be equal to 4 times the initial intensity. Okay, so that's the cause of interference. You can see that there are, so this, if for light the intensity is 0, that means no light, okay, or dark. And um, if the I resultant is 4 times I, it's generally brighter than the original source, right? So that's the interesting effect of interference. After interference, the light can look brighter, and there can be some dark spots. So there will be intermittent dark and bright spots depending on this delta delta. Okay, so now we talked about how interference can appear. It can appear because of phase difference. Okay, so now how could this phase difference appear? Well, you could imagine that there are two rays of light that originally had a phase difference that are interfering. But sometimes this phase difference can happen just because light went through a different path. So for example, in this particular example over here, you see that the first ray of light, which is getting reflected at this first surface, and the second ray of light, which is getting reflected at the second surface and then getting transmitted through the first surface, these two rays of light actually travel through two different paths. And because they travel through two different paths, they will end up having a phase difference. And we'll see how that could appear. Okay, so let me sort of make a different section. We will call this section phase difference due to path difference. Okay, so that's going to be our topic, and we'll talk about how phase and we'll say phase and path relationship. Okay, so let's take a look at the phase versus path relationship, right? And we will just talk about the phase. So what is the phase of, let's say I have a wave that looks like a sine kx minus omega t plus delta, right? So this is the phase, right? That entire thing, stuff within the parentheses, is the phase. This delta is just a phase constant, right? That's just the constant part of the phase, right? But the phase would change as x changes or as t changes. Okay, now generally, because we make measurements at a particular instant of time, this time is the same for all interfering waves, right? So t will not change. But if I look at a ray of light that is interfering over here, that came from somewhere over here, and another one that came from somewhere over here, these two rays of light have traveled different distances, and the first one has traveled um, um, some amount, and the second one has traveled some other amount, and this difference is delta x. So then I can write the second ray of light. So for the first one, so this is for the first one, let's call this A1 is this. So for 2, this is number 2, A2, I'd have to write A sine kx. But now this ray of light has traveled an additional delta x distance, so it's kx plus delta x minus omega t plus delta. Okay, so this full quantity is now the phase, right? So now let's see what this means. So this tells me that this will be a sine kx minus omega t plus delta plus k times delta x, right? So that k times delta x will give rise to an additional phase constant. So this is the total phase constant now. And why is this a constant? It does not depend on x, of course. Delta x does not depend on this final value of the x. The final value of the x is the position over there, and the time at which we are making the measurement, that's the value of the t. But this, because it traveled a certain amount of extra distance, it contributes to the phase constant by an amount k times delta x. So what is the phase difference? Well, the phase difference, delta delta, that is in this case equal to k times delta x. Okay, but remember k is 2 pi over lambda. So this is really 2 pi over lambda times delta x. So generally this is the way to go from path difference to phase difference. This is path difference, right? So that's the path difference. and this is the phase difference. Okay, so path difference to phase difference, whenever we are doing it, we will always do this delta x. Okay, delta x times 2 pi over lambda will give us delta delta. That's the idea. Okay, so there's one more thing though. Let's say that this path difference is happening in a different medium, right? So if I have a medium, so let's say that these two objects are in a medium that has refractive index n, different from one, then what would happen is that the wavelength of light in air versus the wavelength of light in this medium is different, right? So what I should really be using for this lambda over here is the wavelength of light in the medium. So I'm going to call it lambda m, right? Lambda m is wavelength in medium. Wavelength in medium, okay? And how does this figure in? Well, if you think about it, right? Um, when I go from one medium to another, and we talked about this at the beginning of the intro to optics class, what we said is that if, let's say that there is a ray of light that is coming in that has wavelength lambda, and when it goes inside, of course, what mainly changes is that the frequency of light does not change. Frequency stays the same as you go from one medium to another. So this is, let's say, air, and this is medium um, with refractive index n, and I'm considering then that n for air is 1 and medium has a different n, right? That's the idea. These are the two refractive indices. The frequency of light doesn't change. The speed of light for sure changes. The speed of light was c over here, and this is v medium over here. And how is this v medium measured? Well, v medium is going to be equal to c over n, right? Refractive index c divided by the refractive index. The speed of light slows down, it goes down, so v medium is c over n. Okay, frequency stays the same, and we know that the relationship is c equals lambda times nu. So inside the medium, it's going to be v medium is equal to lambda m, which is the wavelength in the medium, times nu. The frequency doesn't change. So then from here, you can work out that lambda m is really equal to, if I divide this equation by that equation, then I get lambda m over lambda. Lambda m over lambda is equal to v medium divided by c, which is 1 over n, right? So then you can work this out, that this means that lambda m is going to be equal to lambda over n. Okay, so then if this kind of path difference from phase difference, or the other way around, phase difference from path difference happens in a medium with refractive index n, what I should really be using is not lambda, not the wavelength of light, but lambda over n. So delta delta in a medium, delta delta medium, becomes 2 pi over lambda medium times delta x, which is equal to 2 pi over lambda over n. N is the refractive index of the medium, so let's call it n medium, times delta x, which is equal to 2 pi over lambda times n medium times delta x. And oftentimes this quantity, n times delta x, is referred to as the optical path difference. Optical path difference. And of course, if you were doing this experiment just in air or in vacuum, this n medium is 1, so the optical path difference and the real path difference are exactly the same. But in general, if you have a medium, then the optical path difference is refractive index of the medium multiplied by the path difference that you can observe. Okay, so that's the idea. So whenever you're finding the phase difference from path difference, what you have to do is multiply the optical path difference by 2 pi over lambda to get the phase difference. Okay, so now let's sort of go back to our thin film discussion. So in our thin film discussion, we have these two rays of light, the rays of light that are getting reflected and transmitted respectively, that are interfering. So now let's figure out what is the path difference between these two rays. Well, although this figure sort of shows oblique incidence, what I really want to consider is incidence at zero angle. So something shown in this figure over here, right? So this figure has normal incidence, So since it has a normal incidence, the reflected ray of light is just getting out over here, and the transmitted ray, which is getting reflected at the second surface, moves an extra path of 2t. So delta x is equal to 2t. But this is where t is the thickness of the medium, right? So let's call this t the thickness of the film, okay? So this additional 2t will give rise to some sort of phase difference, right? But remember, we also have to consider the refractive index of the medium. So in this case, N2 is the refractive index of this medium inside. So delta x is really 2t times N2. So that's the path difference. So what is the phase difference due to path difference? Then we can sort of come up with an expression. Phase difference, okay, phase difference due to path difference for thin films. Yeah, so that part is just going to be equal to delta delta is equal to 2 pi over lambda, where lambda is the wavelength of light, multiplied by the optical path difference. So that's going to be equal to N2 times delta x, which is the actual observed path difference, right? So you could write it as N2 times delta x, where delta x is just 2t. Or you could just write delta x, meaning the optical path difference, which is going to be delta x then equals N2 times 2t. So if evaluating this and plugging it back, we get 4 pi N2t divided by lambda. So that's our delta delta generally. And what is this N2? N2, N2 is material of the thin film, or refractive index of the material of the thin film. And that's the idea for path difference causing phase difference in thin films. Okay, so but this is not enough to deal with our current situation. There's something else that's going on, and we'll discuss this in a second. So we have already seen one source, or actually two sources, of where phase difference can appear from. So we'll see where may phase difference appear, right? So we'll sort of give you a few quote unquote cardinal rules. Number one would be that phase difference from path difference, right? Whenever there's a path difference, that can translate into a phase difference, and the formula for that is delta delta is equal to 4, actually I'll write the actual formula. I will write 2 pi over lambda times delta x, right? So this is the phase difference, that is the path difference, okay? And then the second one was change in wavelength, so difference in medium slash optical path, yeah, slash refractive index. So how does refractive index affect this? Refractive index. Okay, so there the rule is going to be that delta delta is really equal to 2 pi over lambda multiplied by delta x optical, where delta x optical is equal to refractive index of the medium, and medium, multiplied by the observed delta x, right? So for instance, in the case of thin films, so the thin film example was delta x is equal to 2 times t, where t is this thickness, right? T is this film thickness. So 2 times t, but delta x optical is equal to N2, or N medium if you want to call it, N2 times 2t, or N2 times delta x, which is equal to 2 times N2 times t. That's the idea. right? There turns out that there is another source of where phase differences can appear. And so phase differences, the third one is that phase differences may appear due to reflection, And this only happens, and this is crucial, reflection from rarer to denser medium. Okay, what does this mean? Of course, reflection happens when ray of light goes from one medium, reflects on another medium, and comes back to the same medium. So the first and the third media have to be the same because this is reflection. So for instance, over here, this ray of light is trying to enter N2 but couldn't, gets reflected back into N1. Right. So what am I talking about? I'm talking about the interface itself. So whenever you are talking about due to reflection, you would go to the interface and see which two media um, are 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 in question, and you look at where is the incident light coming from and where is it trying to go, right? So if it's coming from rarer and trying to go to denser, then there's a phase change. This is associated with um, a delta delta of pi or 180 degrees from you can say the same thing, but from denser to rarer medium, this delta delta is equal to 0. So this is another um, source of phase difference. And these are the three sources of phase difference that we're going to discuss and that are going to lead to consequences for interference for us. So one final thing that I want to mention before moving on to doing problems is that you should know that there are these three conditions for which a phase difference may appear. But what happens for refraction? Well, for refraction, there's never a phase change. So refraction means delta delta, the associated phase change is 0. And this is for both cases, right? For both cases, and the two cases being when light is going from rarer to denser medium or light is going from denser to rarer medium. In both cases, delta delta, or the change in phase due to refraction, is 0. And this has consequences on the problems that we're going to do. So let's now move on and try to see how all of these effects really affect rays of light coming toward a thin film, and it's upon a reflection from the thin film, how that causes interference. So in order to think about it, let's consider a ray of light. So although I'm drawing it as oblique, we're gonna, when we think about it, we're gonna think about these rays as being near normal, very close to being normal. And the reason why I'm drawing them to be oblique is so that I can distinguish between the different lines that I'm gonna draw over here. But the idea is that this ray of light that is incident over here gets first reflected, right? And then gets reflected from the second surface again, right? So over here it gets reflected, comes back here. Part of this second ray also gets refracted, but if we put our eyes over here, then we are not going to see that ray that went to the other side, right? So this is my eye over here. So the second ray is going to get then transmitted in the first surface and reach the eye. And similarly, the first ray, that a part of it got reflected over here, and that's also going to reach the eye. So these two rays over here can then interfere and form those beautiful patterns that we were talking about before, right? And so we want to figure out, essentially, in order to figure out the patterns that they form, all we have to do is figure out the path difference or actually the total phase difference between these two rays of light. So let's call the first ray 1 and the second ray 2. Then in order to figure out what kind of interference patterns really form, all we have to know is the phase difference between 2 and 1. And why is that? Well, if we go back to our original idea of interference, remember the amplitude modulation, the change in amplitude was coming from this factor delta delta, which is the phase difference. So as long as we can find out the difference in phase between 2 and 1, we're good to go. So what is that delta delta going to be in this case? Well, delta delta, first we have to find the phase of ray 2, right? So let's think about where that phase can come from. Well, it can come from the fact that this ray, so phase differences only come in three ways. One way is due to reflection. Is this second ray getting reflected? Well, it's getting reflected over here, and we will call the associated phase delta 2, right? So delta 2 is a phase for the second ray. What else is happening? Well, the second ray is moving through this medium and back, and so it's going through um, a real path difference of 2t, right? The first ray gets reflected at the first surface, so it doesn't encounter this extra path. So 2t is the actual path difference, but then the optical path difference is 2t times n2. Remember, the optical path difference, delta x optical, is equal to refractive index multiplied by the path difference that you can see in the medium, right? So that's the optical path difference, but once we know the optical path difference, we can figure out that the phase difference is 2 pi over lambda times the delta x optical, right? So this is the total amount of phase, additional phase that the second ray has over the first ray. But remember, the first ray also goes through a phase change, and that's because it is reflected at this first surface over here. And so we have to subtract off that amount of phase change for the first ray. So this will tell us the actual phase difference. This formula here is going to tell us the actual phase difference between the two rays when they're interfering. Okay? So of course, this delta x optical, we can just in this particular scenario just write delta 2 plus 2 pi over lambda, and delta x optical is just n2 times 2t, and so this gives us this formula. And so we can simplify this and write delta is equal to 4 pi. So putting all this together, then we find that delta is really equal to, it has two parts. First is this the phase difference due to path difference, which turns out to be 4 pi n2t over lambda, plus we have this delta 2 minus delta 1. Now this delta 2 minus delta 1, this is a quantity that has to be sort of found out on a case-by-case basis. So let's look at 4 cases. Case number 1 will be when n1 is greater than n2 is greater than n3. So you know, if n1 is greater than n2, then delta 1, which is the delta at this surface, that is equal to 0. And so is delta 2, because now we have n2 greater than n3. So in each case, light is going from a denser to a rarer medium, which tells us that the delta has to be 0. Okay, now case number 2 is just the opposite. So n1 is less than n2 is less than n3. And now you know that delta 1 has to be equal to pi, and so does delta 2, because in both situations, the ray of light that is getting reflected off of a denser medium, right? n2 is greater than n1, so n2 is denser than n1. Case number 3, now we're going to mix and match these conditions. So we'll have n1 greater than n2, but n2 less than n3. And in this case, we know that since n1 is greater than n2, delta 1 has to be equal to 0. But since n2 is less than n3, their delta 2 has to be equal to pi. And finally, we'll have case 4, and case 4 is going to be n1 less than n2, but n2 is greater than n3. And here, the roles of delta 1 and delta 2 are just switched from the previous case, because now delta 1 is going to be equal to pi, and delta 2 is going to be equal to 0. So generally, for thin film interference, then we have 4 cases, and those 4 cases essentially tell you what delta 2 minus delta 1 will be. So in each of these cases, the first 2 cases, we have delta 2 minus delta 1 is equal to 0. And in this case, delta 2 minus delta 1 is equal to pi. And in this final case, delta 2 minus delta 1 is equal to negative pi. Okay, so how does this help us? Well, we know that for constructive or destructive interference, delta has to take a certain form. So we know that for constructive interference, this delta has to be some integer multiple of 2 pi, which means that it has to be some 2m pi, where m is equal to 0, 1, 2, etc. Right? And on the other hand, for destructive interference, this same quantity delta has to be some odd integer multiple of pi, so it has to be 2m plus or minus 1 pi, where again m is equal to 0, 1, 2, etc. So now, putting all of this together, we find the relationships for constructive and destructive interferences as follows, right? So we'll do a sort of constructive destructive table for the two um, equations. So for constructive interference, we will find that 4 pi n2t over lambda plus delta 2 minus delta 1 should be equal to 2m pi. And for destructive interference, the same formula becomes 4 pi n2t over lambda plus delta 2 minus delta 1 is equal to 2m plus 1 pi. Okay, so now these two formulae have to be applied in specific cases. In particular, when delta 2 minus delta 1, that is 0, so that is the cases 1 and 2. So in these cases, these formulae are just 4 pi n2t over lambda is equal to 2m pi for constructive, and for destructive it is 4 pi n2t over lambda is equal to 2m plus 1 pi. Right, but you can now manipulate this equation, and in fact you can see that if you divide both sides by 2 pi and multiply lambda to both sides, we will find that 2 times n2t is equal to m lambda is this one, and the second one will become 2 times n2t is equal to m plus 1/2 lambda. And so this is the condition for cases 1 and 2, and we can continue this with case 3. For case 3, we will find that the left-hand side of this relationship is just 4 pi n2t over lambda plus pi is equal to 2m pi, and that's the condition for constructive interference. And for destructive interference, we'll find that 4 pi n2t over lambda plus pi is equal to 2m plus 1 pi. And now we can simplify both of these relationships. Simplification of this relationship can be done by taking this pi to the other side, right? So this becomes a 2m minus 1 pi. And if we carry that on and divide both sides by 2 pi once again and multiply both sides by lambda, we will find that 2 times n2t is equal to m minus a half lambda. And on the other side, we will find that 2 times n2t is equal to m lambda. Because here, if you notice, the pi's will cancel from both sides. And what we're going to have left over, we can divide both sides again by 2 pi, multiply both sides by lambda. And so this is the relationship. Now I'm going to leave case 4 for you to work out. It's exactly the same as case 1, 2, and 3, except now you have to use a different condition for delta 2 minus delta 1, which is delta 2 minus delta 1 this time is negative pi. But notice what's going on here. For every single case that we have worked out, we have eventually come up with a relationship like this, which equates the path difference to some integer or half integer multiple of lambda. And that's the idea, right? So whenever you have interference, we'll find that the optical path difference, so the left-hand side over here is always the optical path difference, right? This is the optical path difference, and that optical path difference is ending up equal to, depending on whether it's a constructive or destructive interference, it is either a half integer multiple of lambda or an integer multiple of lambda. And that's the idea for interference. We're going to switch gears and talk about a slightly different kind of interference. We'll talk about interference from two slits. So here in this picture, I have a source of light behind this first screen over here. Somewhere over here, let's assume that there's like a bright source of light, and we will think of that being like a laser light. So it has only one color of light that's coming out, and that's the light is allowed to pass through two slits over here in this screen, and these two slits are separated by a distance d. And then further away, let's say at a distance l, from the slits, the horizontal distance is l. That's where a screen is located. And so we want to see what happens. It turns out that each of these sources each of these slits turn out that they start acting like secondary sources of light, and these two lights, beams of or waves of light that are coming out of these two slits act as coherent sources of light, and these coherent beams of light then interfere, and we observe an interference pattern on the screen. And so we'll try to predict what kind of interference pattern is going to be formed. And in order to do that, again, the basic idea for interference is that if there is a path difference between two rays of light that are interfering at the same point, then that causes a phase difference, and that phase difference will lead to a path. In the case of the double slit experiment, this phase difference can be quite easily found. Again, remember the phase difference delta, or delta delta if you like, is equal to 2 pi over lambda multiplied by delta x times the refractive index, but we are doing this experiment in air, so it's air over here. So both paths of light are in air, and hence the refractive index is just 1. So we don't have to include that refractive index over here. Delta delta is simply 2 pi over lambda times delta x. So all we have to do is figure out this delta x, and we are good to go. So how do we do that? So let's look at this picture over here. You can clearly see at this point P, the first ray of light is covering a slightly smaller distance than the second ray of light, right? So if you go back, go to this inset picture over here, what is that distance between the two paths? Well, that's going to depend on the angle theta which each of these rays of light are subtending with a horizontal line. Now, we are assuming that the screen is actually quite far away. So because the screen is quite far away, then L is much larger than Y. So technically, these two rays of light that are coming very close to the slits, they are roughly parallel to each other. And so I can just drop a line, this dashed line, perpendicular to the second line from the first line, and then observe that the additional distance that the second line, if this is line number 1 and this is line number 2, then the second line or the second path of the ray of light is covering a slightly more distance d sine theta, right, where d is the distance between the two slits and this angle is theta. So since this angle is theta and that's the distance, then you can observe that d sine theta in that right triangle, that distance is d sine theta. Okay, so since this distance is d sine theta, that's the path difference. So our delta x here is equal to d sine theta. So if I plug that back into my delta delta expression, I find that the phase difference has to be equal to 2 pi d sine theta over lambda. Okay, and remember, it's when we talk about interference patterns, the intensity of the combined two-ray intensity, if the intensity for each of the rays I1 was equal to, let's say, I0, and I2 was equal to also I0, that's sort of the assumption because they're coming from the same source, so the intensity at the two slits was the same. After interference, I net on the screen is going to look like 4 times I naught cosine squared delta delta over 2, right? That's the idea. And so delta delta over 2 is the relevant quantity. So if you just try to find what delta delta over 2 is, that delta delta over 2, that quantity from here is just going to be pi d sine theta over lambda. Okay, and we know that the conditions for constructive and destructive interferences are. For constructive interference, we will find that the condition that we need is delta delta over 2 has to be either 0 or pi or 2 pi, etc., which in other words, this is just an integer multiple of pi. And so m pi, where m is an integer. And how do we see that? Well, go back to the net intensity equation. Here, within the brackets is delta delta over 2. If this stuff that is inside the bracket is 0, pi, 2 pi, etc., then cosine of that is going to be plus or minus 1, which means that the cosine square is going to be plus 1, giving a large intensity, 4 times the intensity of each of those sources, right? So that's the idea of constructive interference. And now we can also talk about destructive interference. And for destructive interference, what we need is this delta delta over 2 to be equal to pi over 2, 3 pi over 2, etc., which is the same as saying it's m plus 1/2 pi over 2.
or m plus 1/2 pi, where m is 0, 1, 2, etc. Right? So these are the two conditions, and if I take these two conditions and I plug it into that equation, then immediately we find that pi d sine theta over lambda is equal to m pi is the condition for this first part, the constructive, and for the destructive part, we find pi d sine theta over lambda is equal to m plus 1/2 pi. And of course, one can just remove the pi's from both sides and multiply both sides by lambda. So that will give us d sine theta is equal to m lambda for constructive, and d sine theta is equal to m plus 1/2 lambda for destructive. So what is this telling us? Well, this is telling us that if the path difference is some integer multiple of lambda, right, d sine theta is the path difference, delta x, right? So if the path difference is some integer multiple of lambda, we get bright spots on the screen, right? And if the path difference is some half integer multiple of lambda, then we get dark spots, right? And what is the intensity of the bright spots? The intensity of the bright spots is 4 times I naught. And what is the intensity of the dark spots? That's just 0. It's that if I put in delta delta over 2 equals some half integer multiple of pi, you see that cosine of that will always be 0, which means that the intensity, net intensity, is going to be 0. And this is kind of a cool thing that goes on, and we've seen these in um, demos in class. And this is essentially the idea of interference from a double slit. Now, there are some additional things that we can do with this problem. So one of the things that we can do is we can, in terms of theta, y, and L, relate relate theta, y, and L, and where y is really the position of a dark or a bright, and in this case, these are referred to as fringes on the screen. So if we talk about y, how is y related to everything else? Well, we can look at this triangle, and we kind of know tangent of theta is roughly equal to y over L. And since theta is small, so because theta is small, we also know that tangent of theta is roughly equal to sine of theta because theta is small. So this is also roughly equal to theta, right? So now sine of theta is related to the dark and bright fringe positions because these appear in the constructive and destructive interference conditions, right? So we can sort of backtrack. So we can sort of say that y is equal to L tangent theta, which is roughly equal to L sine theta, which is equal to L over D times delta x, or D sine theta. And then this would imply y is roughly equal to L over D times m lambda for constructive interferences, so bright spots, and y is roughly equal to L over D times m plus 1/2 lambda for destructive or dark spots, right? So now um, knowing L and D and lambda and M, we can figure out the position for Y, right? And so one thing that we could immediately see is that if I plug in M equals 0, the only way this can happen, because D and lambda are not 0, we know that M equals 0 will lead to theta equals 0. And this can only happen for the constructive case, because if I plugged in M equals 0 over here, then I will find that D sine theta is equal to 1/2 lambda. So theta has a positive value, which means it's not exactly at 0. So the dark spot is not exactly at theta equals 0, right? So if I plug in M equals 0 over here, for instance, right, I'll find that sine of theta is some value lambda over 2D. So clearly this angle is not 0, and hence it's not at the center of the screen, right? So at the center of the screen, then what we find, that is theta equals 0 is where the center of the screen is, right? So this theta equals 0 will also lead to y equals 0. That's a bright spot. So at the very center of the screen, we find a bright spot. And then as we go further out on both directions, we see alternating dark and bright spots, right? And so we can essentially figure out the distance between, let's say, two bright spots, and that's quite simple to do. So we have labeled the constructive or brights on the screen by ym is roughly equal to, like we found, m lambda L over D, right? So then we can also find sort of the bright thickness. Um, in this case, this is going to be roughly equal to m plus 1 lambda L over D minus m lambda L over D, which is equal to lambda L over D. Okay, and we can do the same thing with the darks. So darks are at ym is equal to m plus a half lambda L over D, right? The m changes to m plus a half over here, and so y is L times lambda over D times m plus a half, which means that the dark thickness, um, so distance between two consecutive dark bands, which is really the bright thickness, so that's what we're calling dark thickness, is going to be equal to m plus a 3 halves. So I just added 1 to m lambda L over D minus m plus a half lambda L over D. So if we subtract, the m's go away, 3 halves minus a half will give me a 1. So I'll again get the same result, lambda L. So we are finding that these fringes are essentially of the same thickness and equidistant from each other for a double slit pattern. Okay, so this is sort of an introduction to interference. The next topic that we will talk about would be diffraction of light and a combination of diffraction and interference.